in there, so it's kind of like a positive kind of sign. Because a negative charge is an anion. All right? So if an atom has gained one or more electrons, now it's an anion, a negative charge. So for you to understand this, it's something like this. If I have some element that has a negative and a positive, so we have, I don't know, we'll say 6 negative charges, and here's positive. So the positive is going to be protons. So there's 6 protons over here, which, let's just be, so one has 6. Oh, carbon, I should have known that. Okay? So let's say this is carbon. It has 6 negative over here and 6 positive. But what's going to happen here, we have electrons here and we have positive over here. So if I lose an electron, that makes this whole thing positive or negative? Positive. So you lose an electron, you become positive. Okay? If I gain an electron, so we'll gain it. If I gain an electron, does it become negative or positive?
Negative.
Negative. You see how that comes in? It took me a long time to come up with that instead of just memorizing it. You get to see it. This is Common Core math, the new math. You could see this instead of just memorizing. Okay? Do you understand that? Okay? So keep that in mind. A cation is always going to be positive. It's because we lost an electron. An anion is always going to be negative. That means we gained an electron. All right? A happy cat, a positive cat. Think of it like that. Okay? And this is just kind of like showing the same thing over here. When you lose an electron or gain an electron. All right? So, we have, these are the ones you should memorize, okay? And we're going to utilize this quite often. Intracellular fluid. Inside the cell, the major cation is going to be K, which is potassium. All right? Just have to memorize potassium. It's kalemia. That's what it stands for back in Latin times, but they kept it there. The major anion is this little messy thing called a phosphate. So inside the cell, we are going to be loaded with potassium and loaded with phosphate. Outside the cell, and plasma and interstitial fluid are similar, except that plasma has more proteins. It's kind of a FYI kind of thing. All right, you'll learn more about that in A&P2. But outside the cell, there is going to be more sodium, it's the major cation, and for anions, the major one is going to be chloride. You need to memorize this. When we get into action potentials, this is really going to make a difference. So you got to really memorize this. So I came with a little mnemonic to help you out. All right. I didn't do this before, did I?
Yes, you did.
Yes.
Oh, I did?
Yeah.
Oh, okay, so salty banana, okay? I did do this, I'm sorry for, but again, the banana is loaded with what? Potassium, okay? So the banana is your cell, so it's loaded with potassium. You're putting salt on this. Salt is usually what? Sodium and chloride for that matter. So outside the cell is going to be loaded with sodium and chloride. The only one you got to memorize is the phosphate, but that makes your life a little bit easier. You just got to memorize one thing. Okay?
So outside the cell?
Outside the cell, extracellular fluid is going to be, the high things are going to be sodium and chloride. Inside the cell, it's going to be loaded with potassium and phosphate. Okay? So that's where I came up with that thing. And so potassium, since it's more there's more inside than outside, potassium wants to go from a high concentration to a low. So if the potassium gates of the cell are open, it wants to pour out. And if the sodium channels are open, it wants to pour in. It's going to go from a high concentration to a low. Okay? That's the basis of what we're going to talk about with the action potential in a few weeks.
What's the ECF again?
ECF is extracellular fluid,
And IF?
is intracellular
No,
fluid.
I mean IF.
Oh, this is interstitial fluid, which is basically fluid in between the cells. So we can have it like in the blood. There's a lot of places that fluid could be outside the cell. In our eyeballs, in our knee joints, in between cells, in the blood. These are all outside cells. But we have some that's going to be inside the cells, and that's the intracellular fluid. Okay? Questions about that?
Is the banana supposed to be
cell.
potassium and phosphate?
Inside, yeah.
Oh, and
Yeah, I don't. Yeah, the phosphate too. Yeah.
Okay.
Now there's other things in there also, but I'm just giving you the major cation, the major anion. Is there sodium inside the cell? Yeah. It's just that there's more sodium outside than inside, and there is potassium outside, but there's just more inside. All right. All right. Now we have chemical bonds here. All right. Once you learn about the elements, then how can we put elements together? We're going to glue them with these bonds. And there's three types of bonds. There's ionic bonds, covalent bonds, hydrogen bonds. We don't call them James Bond because it's just not a bond these days. Although I think he's one of the best agents. No, okay. So we have three different bonds to be concerned about. And yesterday we talked about some of these over here. But now it'll make more sense. Ionic bonds are bonds that are attracted between two, like magnets. A cation and an anion, a positive and negative. And they exchange one or more electrons between the atoms. They're weaker than covalent bonds, which we'll talk about. So a good example of this is sodium and chloride. They're attracted to each other. And they exchange one electron for another, okay? And because of that, they're attracted to each other. You can pull them apart, they're like magnets, but they're pretty strong. But they're not as strong as super glue, okay? So it's kind of like doing this kind of thing. They kind of exchange that on there, sodium and chloride, okay? Then we have covalent bonds. These are the strongest of all bonds. Covalent bond is sharing one or more electrons between the atoms. All right, not exchanging, sharing. This is the strongest of them all, and a good example of this is a water molecule. You have one oxygen, you have two hydrogens. They are glued together with super glue. You can't break them up. You need special things, hydrolysis machines, electrohydrolysis machines to do that. We can have a single covalent bond, and that's sharing one pair of electrons. We could have double covalent bonds, where we're sharing two pairs of electrons, and we could even have triple covalent bonds. Not as often seen, but they are there, and we're sharing three pairs of electrons. So it's doing this kind of thing, bam, and you're sharing a pair of electrons, one from one atom and one from the other atom, or I'm sorry, element. Okay, just kind of putting it together like that. So we could have methane gas, which is CH4. So it's this. So you're going to be sharing one pair here, one pair here, one pair here, one pair here. But between here, that's one single covalent bond, one single covalent bond, one over here and one over here. So we make it a little bit easier by just putting a stick there or a line there, so it's easier to draw this, show it like this. One single covalent bond in there. Now here's a little rule. Carbon is going to be a key to understand organic chemistry. And carbon always, always, always will have 4 covalent bonds attached to it. I don't care if they're double bonds or single bonds, they will always have 4. And chemistry will explain all about that. I just don't want to go into details. That's something you just memorize, and it'll make your life easier when you get in organic chemistry. Always, always, always. We could have a double bond, like I showed you before, oxygen, and you're going to be sharing 2 pairs of electrons between 2 elements. And you could also have nitrogen gas, which has 3 pairs that are being shared, and we represent it with 3 lines like that. Okay? These are the strongest of them all, is the covalent bonds. Now, covalent bonds could be nonpolar or polar. Nonpolar is sharing of electrons that is equal. Polar covalent bonds is that the sharing of electrons is unequal. When I did this before with water, I drew it like this because the hydrogens are kind of pulling it down before, and it's not giving the oxygen what it's supposed to. And because of that, it's not equal. Okay? Carbon dioxide is equal. They're sharing on both sides. You just have to memorize which ones we're going to talk about. It's not too heavy in A&P to understand polar and non-polar. Bless you. But when you get into your chemistry later on, yes. All right? But I want to just introduce you to that. All right? One atom is going to attract the shared electrons more than the other. So if we increase the strength, ionic bonds are strong, polar covalent bonds are stronger, but non-polar covalent bonds are the strongest. And these are the examples I kind of put with you so far. All right? So non-polar, if you know that something's a non-polar covalent bond, it's extremely strong. Okay? Very difficult to break that. Then we have hydrogen bonds. Yes?
See, like if I was looking at that, those 2 molecules, right?
Mm-hmm.
I feel like I would say that H2O is like nonpolar because there's 2, right? Doesn't it divide it equally? But you're saying it's
No, it's not
polar.
dividing. It's just that the hydrogens are, this hydrogen is sharing with this oxygen. Okay? This hydrogen is sharing with this oxygen. For some reason, the hydrogen is pulling, it's sharing it more. I'm sharing my Snickers bar with you, but I'm going to get the bigger half. You see what I mean? It's not being shared equally between these 2 and between these 2. So it kind of pulls down a little bit more. Whereas the Snickers bar is cut in half equally. It's just something, just respect kind of thing. Those probably spent a whole period talking about this stuff in chemistry. I'm just touching on it, all right? Just to show you that there is differences on there, okay? Which is why when you see this kind of stuff in anatomy and physiology, why we're seeing some that are bent and some that are not, it's dealing with the polarity of this. I don't want to go with heavy stuff, just so you can appreciate a little bit. And then we have hydrogen bonds. And hydrogen bonds are the weakest of all the bonds that we have. Okay? They're only about 5% of the, that's a typo, it should be strength, not strength. I gotta fix that, I just noticed it. After 8 years, I just noticed that. But it's very weak, okay? It's only about 5% strength of covalent bonds. They're really only there for structure reasons. To give it like the structure, to give it a 3-dimensional kind of thing. But they're very easy to break. We kind of showed that when we dealt with the DNA, right? Where the backbone, the sugar and phosphates on the sides yesterday, they're put together by covalent bonds. Very difficult to break up. But between the bases, adenine and thymine and cytosine and guanine, that's being put together by 2 or 3 hydrogen bonds. And you can see through those enzymes, we could very easily unzip it and very easily put it back. So it's just there to give it like a 3-dimensional kind of thing. It's not very strong. It's there, but it's not very strong. So it's also responsible for surface tension on water. You ever put like a paper clip on top of the water very delicately and it's sitting on top? Or those bugs that can actually sit on top? That's a surface tension. You push that bug, it'll fall right through. All right? The surface tension is also based off of hydrogen bonds. It's not very strong. It's there if you put something light, it's fine. But like I said, it's going to create more of a 3-dimensional kind of figure. Okay? And it will bond to something that's going to be oxygen or nitrogen. So let me show you what's going on here. All right? It's going to link with molecules that are distant and create this, and I'll show you a picture of it. They're intermolecular bonds, not intramolecular bonds. So let me explain what this is. I can erase my beautiful picture of the... Okay. When we deal with water, water is made up of covalent bonds. So, water's here. We could have another water molecule over here. We could have another one over here. Another one over here, and so forth. Now these bonds between the oxygen and hydrogen, they're what kind of bonds?
Polar, right?
Covalent. Just say covalent.
Covalent.
Don't worry about nonpolar polar. They're covalent bonds. Is that strong or is that weak?
That's very
In the
strong.
middle.
Very strong. Okay? Now, we also have hydrogen bonds when we have water, meaning there's going to be a bond between oxygen and hydrogen. There's going to be another one over here. Another one over here. This is creating a 3-dimensional figure. We could easily break these. Okay, like surface tension. We could break those, that's no problem. We can't break these. We need special machines to do that. The covalent bonds are intramolecular. The hydrogen bonds are intermolecular. Now, what does that mean? Intermolecular means in between molecules. Intramolecular are in between elements of the same molecule. Take, for instance, the word intramural sports. Intramural sports are sports that are played in the school. The science department of CCM is going to battle with the English department at CCM. It's intramural. It's within the same college. It's within the same molecule. And then you could have intramural. You don't call it that, but you can. Intramural sports is that CCM is going to battle with Sussex County Community College. Now you're actually playing against different schools, different molecules. Does that make sense? All right? Intramolecular versus intermolecular. Yeah.
So intermolecular are always hydrogen bonds, right? For our sake.
Say that again?
Intermolecular are going to be hydrogen bonds always for our sake?
Yes.
Yeah.
Mhm.
Okay.
Yep. All right? So ionic and covalent bonds are intramolecular. Okay? And like I said, it helps create, the hydrogen bonds help create this 3-dimensional structure. That's what, if you saw a DNA molecule, like I said, it's a double helix. It's a spiral ladder. The spiral thing is a three-dimensional thing. It's because of the hydrogen bonds between the bases that are creating that. If we didn't have the hydrogen bonds, it would just be a linear thing. So a three-dimensional thing is created by the hydrogen bonds. Okay? So again, this is a polar molecule. The